Hi everyone, my name is Mrs. Fitzpatrick, and today we are going to be talking about convergent and divergent series. We're also going to specifically dive into utilizing the geometric series as well as the nth term test to determine if those specific types of series either converge or diverge. All right, so let's start with the definition of a sequence because there's some things links in particular between sequences and series. Okay, so a sequence, if you remember, is an ordered list of numbers. In this lesson, we're working with series, which basically means it's the sum of these numbers. So we're adding up all the terms in the sequence. An infinite series can be represented we're going to use sigma notation. So it's just the sum from n equals 1 to infinity. Notice it's an infinite number of terms that we're going to be adding up. And we are adding up the terms in our sequence, which we use a sub n. So it means you're taking the first term, then adding the second term, then adding the third term, which would be a sub 1 plus a sub 2 plus a sub 3, right? And so on and so forth until we get to like the nth term, right? And then we keep going on and on and on. Okay, so what happens as more and more terms of a series like the sum from n equals 0 to infinity of 2n plus 1 are added together? So we're going to actually look at an example of this. Okay, so looking at the sum from n equals 0 to infinity of 2n plus 1, you get the term. So if you plug in 0, you get 0 plus 1, which is 1. We add it to the next term, which would be 2 times 1. 2 plus 1 is 3. So actually what's happening is we're adding up all of the odd numbers. 1, then 3, 1 plus 3 plus 5 plus 7 plus 9, right? We're going to keep going in that same pattern. Well, this is going to actually go off to positive infinity because if you keep adding up terms that are increasing without bound, that's our new phrasing that we learned last class when we talked about the sequences converging or diverging and whether or not they're bounded. Well, this is unbounded. It's the terms are going to keep getting larger and larger without bound. So what happens is it goes off to positive infinity. Because the terms of this series are increasing without bound. Okay. When this happens, this series is called divergent. Whoops, divergent. It's a divergent series. So this series diverges. Okay, let's look at another example. What happens as more and more terms of the sum from n equals 1 to infinity of 3 over 10 to the nth power are added? Well, let's actually look at these terms. So we plug in 1, we get 3/10, right? We plug in 2, we get 3 over 10 squared is 100, plus 3 over 10 cubed is 1,000, plus dot, 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 dot. Okay. Well, this is 3/10 is 0.3, right? Plus 3/100 is 0.03, plus 3/1000 is 0.003, plus dot, dot, dot. Okay, well, this is interesting. It looks like this is actually 0.33 repeated. Well, what does the number 0.33 repeated equal? Well, that equals 1/3. So it turns out this infinite series converges to 1/3. And so this is an example of a convergent geometric series. And so it is extremely possible to add up an infinite number of things, right, and get a finite value. Because what's happening here is actually these terms are bounded, right? The terms are decreasing and they're bounded because if I take the limit as n approaches infinity of 3 over 10 to the nth power, that equals 0, right? These terms are getting closer and closer to 0. Okay, so let's talk specifically about geometric series, which it turns out number 2 actually was a geometric series. So we need a little bit of vocab first. Let's talk about the first piece of vocabulary. If consecutive terms in a series have a common ratio, this is one of the key vocabulary words when it comes to geometric series. And we call that common ratio R. We use the variable R. The series is called a geometric series. So here's the general form. You will have the sum from n equals 0 to infinity. It doesn't actually have to be indexed at 0. It can be indexed at whatever you want it to start at. In this case, it's being indexed at 0. And it's of a times r to the nth power, where r is that common ratio. In this case, because if you plug in 0 for n, you get a times r to the n. Your first term is actually a, okay? And so when we expand this out, you get a plus a times r plus a times r squared, right? Plus a times r cubed plus dot, 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 a times r to the nth, right? Dot, 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 okay? Now, this is called the geometric series test. This is how we test to see if this series converges or diverges. This is the first test, and we abbreviate it as GST, that you're going to learn to figure out the convergence of geometric series. I think that there's 12 of them. There's a lot that we're going to compile through our time together. Okay, so here's what it states. If the absolute value of r is greater than or equal to 1, then the geometric series diverges, okay? However, if your common ratio, absolute value of your common ratio r is less than 1, this actually means that if your common ratio is between -1 or 1, right? You can also think of it in that way. Therefore, the geometric series converges. And we actually have a formula to what it converges to a over 1 minus r. Now, a is the first term, and r is the common ratio. Okay? All right, so let's take a look at some examples of geometric series. Okay, so we have a few examples here. So we're going to determine if these series converge or diverge, and if possible, we're going to find the sum of the series. So let's take a look at number 1. We have the sum from n equals 0 to infinity of 3 over 2 to the nth power. Now, what we want to do is actually rewrite this in a way that it looks like the form for geometric series. So we can rewrite it as the sum from n equals 0 to infinity of 3 times 1 over 2 to the nth power, right? We can pull that 3 out. We have 1 over 2 to the nth, which really is a half to the nth power. So now it's really clear that your common ratio r equals 1/2. And so therefore, the absolute value of r, which is the absolute value of 1/2, is in fact less than 1. So we are good to go. Therefore, the sum from n equals 0 to infinity of 3 over 2 to the n converges. And let's go ahead and find the value. So the sum from n equals 0 to infinity of 3 over 2 to the n equals, we're going to use our formula. It's the first term, so if you plug in 0 for n, you get 3 over 2 to the 0, which is just 3, so 3, divided by 1 minus r, which is your common ratio, 1/2. So you get 3 divided by 1 minus 1/2 is 1/2. 3 divided by 1/2 is 6. So therefore, this geometric series converges to 6. Also, a little out of practice, but I just realized you have to state the test used. So it converges by, and you can abbreviate it as GST, geometric series test. So whenever you tell me that a sequence or series, converges or diverges, make sure you tell me the test used. In this case, it's the geometric series test, GST. Okay, let's look at number 2. This one's actually already written in geometric form, and your r is 3/2, right? We have 3/2 to the n. Well, the absolute value of r, which is the absolute value of 3/2, well, that's actually greater than 1. So therefore, the sum from n equals 0 to infinity of 3 over 2 to the n actually diverges by the geometric series test. Okay, so now go ahead and pause and try number 3 and 4 is a little tricky. Once you finish, go ahead and unpause and we can go through it together. Okay, let's take a look at number 3. So we are looking at the sum from n equals 1 to infinity of 4 times negative 1/2 to the nth power. So what you want to do is first we can actually easily identify r is negative 1/2. And so we want to check what's going on with the absolute value of r? Well, we have the absolute value of negative 1/2, which is 1/2, and it is less than 1, right? So because the absolute value of r is less than 1, it means the sum from n equals 1 to infinity of 4 times negative 1/2 to the nth power actually converges, and that's by the geometric series test, which means we're actually able to evaluate the sum from n equals 1 to infinity of 4 times negative 1/2 to the nth power equals, now the first term, be careful, it's indexed starting at n equals 1. So if I plug in 1 for n, I get 4 times negative 1/2. My first term is negative 2, divided by 1 minus r, which is negative 1/2. So I get negative 2 divided by 1 minus negative 2, or negative 1/2, turns into a plus. So we have 3/2. We multiply by the reciprocal, and I have negative 4/3 is our solution to that infinite sum. Okay, so the last one, it says, find the fraction form of the repeating decimal of 0.08 using a geometric series. Okay, so first, let's look at the number 0.08 repeated. That equals 0.080808, right? It keeps going. And so if I write this out using a sum, it would be 0.08 plus, now be careful here, it's 0.0008, because notice the next time an 8 appears again, we have 3 decimal places in front of it, right? And so then I have my next one would be 0.0001. 0, 0, 0, 0, 0, 8, right? 1, 2, 3, 4, 5, make sure I got that right. Zeros, right? And it would keep going. Okay, so let's take a look at this. And I think it's easier to do it in fraction form. And so think of it as 8 100ths, right? Plus 8 over its 10 thousandths, right? Plus 8 over, let's see, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, plus dot, 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 right? So what we want to do is we want to look at this and we can write this in a geometric series. So 0.08 repeated equals the sum from n equals, let's just index it at 0. It's just easier to do it when you're writing it yourself. I'll show you why in a second. Because when you index it at 0, you can just take your first term, which is 8 over 100, and then multiply it by your common ratio. Well, if you notice, you're multiplying each time by 1 over 100. So it's 8 over 100 times 1 over 100 to the nth power. So we can actually find the exact fraction of 0.08 because we know that this is a geometric series that converges because the absolute value of 1 over 100 is less than 1. And so we can use our formula, and actually, let's show that step, right? So the absolute value of r, which is the absolute value of 1 over 100, which is less than 1, right? So therefore, the sum from n equals 0 to infinity of 8 over 100 times 1 over 100 to the n converges by GST. Okay, and so 0.08 repeated just equals your first term, which is 8 over 100 over 1 minus your common ratio, 1 over 100. So we get, 8 over 100 over 99 over 100 multiplied by the reciprocal, and you end up with the exact fraction 8 over 99. Punch that in a calculator and you should get 0.080808 repeated, right? Okay, let's go ahead and now move on to the nth term test of a series. Now, be careful because this only proves a certain thing about series. So let's talk a little bit about the nth term test, and I like to call it the nth term test for divergence because it really doesn't prove anything about convergence. Okay, so nth term test says, in general, convergence of a series is less simple than convergence of a sequence. The sequence a sub n equals 1 plus 1 over n converges because the limit as n approaches infinity of a sub n is equal to, well, 1 over n as n approaches infinity, that's going to 0. Plus 1 is just 1, right? So we can say that that converges. Now, the series, the sum from n equals 1 to infinity of 1 plus 1 over n would be 1 plus 1, plus 1 plus a half, plus 1 and a third, plus 1 and a fourth, right? It would keep having that pattern. It actually doesn't converge. And so a series cannot converge unless the terms approach a limit of 0. Okay, so let's go ahead and write down the nth term test. Now, I like to write it as the nth term test for divergence because it does not prove convergence. Okay, so it states if the limit as n approaches infinity of a sub n does not equal 0, then the series, the sum from n equals 0 to infinity of a sub n diverges. Okay? Now, note this test is inconclusive if the limit as n approaches infinity of a sub n does equal 0. Okay, so it does not, in other words, this test does not prove convergence. Okay, so be extremely careful. If your limit as n approaches infinity of a sub n equals 0, this test, throw it out. You have to use something different, and we're going to get a lot more tests. Don't worry, there will be plenty to pick from. Okay, but this is by far the easiest test. So always start here, because if it doesn't equal 0, then you're good to go. You can say it diverges. And you can actually abbreviate it as NTT, nth term test. That's usually how I write it, nth term test. Okay, anyway, let's go ahead and look at an example. So it says, show that the sum from n equals 1 to infinity of n factorial over 2n factorial plus 1 diverges. Okay, so we're going to take the limit as n approaches infinity of n factorial over 2n factorial plus 1. Okay, so this is where that plus 1 is very, very insignificant when we're talking about a limit as n approaches infinity. That 2n factorial is growing so quickly that that plus 1 is not going to impact the value of this limit. So you could actually write this as the limit as n approaches infinity of n factorial over 2n factorial, which actually just equals the limit as n approaches infinity of 1/2, right? Those guys cancel out. Therefore, the limit equals 1/2, which does not equal 0. Okay, so therefore, the sum from n equals 1 to infinity of n factorial over 2n factorial plus 1 diverges by the nth term test, or NTT. Okay, so that's pretty much it. I mean, nth term test, it's super simple. All you do is you take the limit as n approaches infinity of the rule. If it doesn't equal 0, you are great. You just say it diverges by the nth term test. But be careful, because if it does equal 0, then the test is actually inconclusive and you have to use something else. Okay, so that's it for this video. Thank you very much.